Thanks for this great introduction here. Yeah, so I'm going to present some work that started quite a long time ago during my PhD, and we're about to wrap up quite soon. So a lot of research on human learning, including my own, so research on human learning and exploration and curiosity has used tasks like this, where an individual interacts repeatedly with a small set of possible options. It's often done in kind of laboratory or online settings, but a lot of human learning doesn't occur in these situations of imposed isolation, but rather occurs in social contexts where we learn from and our actions also inform other people's actions. And so what this work tries to do is to take a lot of my work on human learning and bring it back into its natural social context. And social learning can be phrased as a form of collective search, where a lot of tasks such as developing new technologies, figuring out which stocks to invest in, or coming up with new scientific innovations can be understood as a type of search on a fitness landscape, where different individuals are all trying to find different locations on this landscape to acquire rewards, and where there's two main pathways for acquiring solutions: through individual innovation, through trial and error learning, or through social imitation. I know this is about simplifying social learning quite substantially, but we can assume that this is kind of a nice starting point to study this. And one paradigm that a lot of animal researchers have used to study this combination of individual and social learning is the producer-scrounger paradigm, where the word scrounger, for some of you who are not familiar, is somebody who borrows from or lives off of others, right? So we have one producer here who finds new patches or new sources of reward, and these other scroungers are then imitating and copying, borrowing from these solutions. This is an example of what a producer-scrounger task looks like when studied with birds, where these different holes can potentially contain food pellets. So they can potentially be patches for rewards. Here you see that one patch has been found, and there's many scroungers then have come to acquire those rewards. The reason that these types of problems are widely studied is that they give some insights into this question of how do we acquire the right balance between individual and social learning. So this is sometimes quite well illustrated with Rogers' paradox, where social learning has frequency-dependent fitness. What this means is that the fitness of using a social learning strategy depends on what everyone else in the population is doing, the people interacting with. Right, so let's assume a very, very simple situation where you can either be a social learner imitating others, or it can either be an individual learner completely ignoring social information. And in this case, if we're in a population, right, where there's no other social learners, so very far on the left side of this axis here, then there's a lot of fitness for being a social learner. There's a lot of people we can scrounge from, right, we can imitate. But as the population shifts to the right here, where we have a population of 100% social learners, then everyone is just imitating one another, right? We're just copying one another and creating these information feedback cycles. So the best strategy in Rogers' paradox is to do something in between, right? To have a mixed strategy, to have a mixed population, where we have a combination of both individual and social learners. This also generalizes to more sophisticated social learning strategies where you can have a combination of both, not only deterministically a social learner or individual learner, be a mixture of both or some sort of hybrid. And often you also find these kind of hybrids will evolve these similar weights. Now, the question I want to ask here is, how do groups collectively negotiate this balance? This balance also will change with different types of reward learning environments, so different reward structures. And different settings will have different benefits for social learning versus individual learning. And I want to ask, can people adapt their social learning strategies to these different types of reward environments? So a lot of previous work have studied human collective search in virtual environments. Some work like Rob Goldstone has looked at how people controlling these like little avatars move between different food patches, which differ in terms of their kind of the skewness of their reward distributions and whether or not the location of these patches are visible or invisible. So they're more dispersed when the exact location of these patches are unknown. And some work by Peakscraft has also looked at replicating some work in fish schooling models by Ian Cousin and collaborators, where there's a hidden reward environment that's spatially structured, and individuals only see what rewards are at their specific location, and they form a form of collective sensing. And so what we're doing here is that we created a collective foraging task in the game Minecraft, where this realistic field of view creates this really nice attentional trade-off between individual learning and social learning. You can either focus on individual search, or spend a costly attentional effort to look at other players to acquire social information, which can be used to then used for imitation. We get these really rich and dynamic social interactions through spatial positions and also visual gaze data as well. So I'll just kind of skip ahead and show you this is what one round of the task looks like. So the task starts with interactive tutorial where participants are taught the dynamics of the task. They're taught how to smash a block, which is by holding the mouse for 2.25 seconds. They're taught that some blocks contain rewards, some blocks don't. Rewards are indicated by this blue splash here. And they're also taught about different reward distributions. So here we've mapped these green watermelon blocks to the smooth reward distributions. But they also learned that there's pumpkin blocks, which are mapped to random reward distributions. So these black pixels indicate reward, and a white pixel indicates no reward. Okay, so this is kind of a top-down perspective of what these melon fields look like. Where these smooth environments, there's these clustered reward structures where finding one reward predicts other rewards nearby. But in the random environment, there's no spatial structure at all, such that there's no value for social information. Seeing someone find a reward is not predictive of other rewards nearby. But in this, if you see someone finding rewards far over there, you can go over there, imitate, and look forage other blocks nearby. So after this tutorial where they're taught the dynamics of the task, they play 2 practice rounds. So these practice rounds are the exact same dynamics as the rest of the task. Each round takes 2 minutes, and they're trying to acquire as many rewards as possible. So participants are incentivized to find as many rewards as possible. Then we have 16 rounds, which is the main experiment that we'll be analyzing. And this is based on a 2x2 within subject design. So participants are either searching in solo environments or in groups. So solo, they're playing on the same field replicated in different locations. So there's no social information, so no social interactions possible, but they're searching on the same reward structure. And the group rounds, they're all searching the same field. They can see one another. They can interact based on visual and spatial interactions. Then the reward environments are manipulated to be either smooth, which are the structured environments here, or random. These are counterbalanced order, but they're always played with 4 rounds of the same type in a row. Okay. So in 2021, we published a proceedings paper with a really small sample that we had to stop collecting data due to COVID back in the early stage of the pandemic. But since then, we made some minor tweaks and we collected the full sample once we were able to run lab studies again. So participants are sitting at computers in the lab. They're not able to see one another's screens. Sound is turned off. So this is really like a psychophysics style experiment. We're really trying to make good use of the rich visual field data. Some minor tweaks we made was that we removed this persistent reward info that was in the previous task. So in this previous version, you see that once you find a reward, there's these blue underblocks. We removed this because we wanted to make social information more fleeting. If you don't spend the time to look at somebody else when they find a reward, you won't know that there's a reward there. So we want to really incentivize this. We added these randomized name tags above players. They're just a random set of alphanumeric characters, and that this allows for the possibility of being selective. We wanted to make this possible. And we also simplify the reward animation a bit. So now it's just a splash. Before, there's also this kind of rocket animation. So we have 2 main hypotheses, but there's still a bit of ambiguity in terms of how to interpret it directly. The first hypothesis is that participants will adapt their learning strategy depending on the environment, whether or not social information is useful in these smooth environments or whether it's useless in these random environments. But we're still a bit unsure about how much they'll adapt and which types of biases will persist. The second question we wanted to ask is, the second hypothesis is that participants will achieve some intermediate balance of social learning and individual learning. This is predicted by Rogers' paradox. But it's unclear what this balance will look like. Will it be the homogeneous balance where everyone has a mixture strategy, or there will be diversity and specialization in these groups? So I'm going to start with the behavior results. Then I have some computational modeling, and then I'll briefly tease some agent-based simulations that we're still working on. So I'm going to start by looking at performance, where here I'm showing you the average reward across these 4 different conditions. So each dot is a participant. And as a statistics framework, we're using these kind of Bayesian mixed effects regressions, where I'm reporting kind of the population level effects, right? So we're controlling for individual differences and also group level differences. So each session may be more similar to one another. So we're controlling for this. So we find very clearly that in these smooth environments with structured rewards, participants are performing much better, right? So these are kind of really reliable effects. In the square brackets, these are the 95% confidence interval. If these don't overlap with 0, it's a reliable effect. We also see a small decrease in the amount of average reward for groups, but this is based on the fact that there's extremely more reward depletion in these group rounds, right? So here I'm showing you the expected reward rates on the right here, where this is the probability that a random remaining block contains a reward. And because people are finding a lot more rewards in smooth environments, and there's more people finding the same finite amount of rewards in group environments, the depletion is much stronger in these group environments. So when we normalize for depletion, we find that there's actually no difference between group and solo relative to this kind of this baseline. And that the main variable is just the fact that is the key difference in terms of reward rate is just based on smooth environments. So these are the regression coefficients here, right? So that's the key variable. Now we see that these reward structures also really influenced different types of search patterns as well. So here I'm plotting the average pairwise distance between players. So note that I can plot this in the solo environments as if they were in the same field, but they're actually in different fields, right? So this is a nice baseline where we control for the structure of the environment. And what we see is that we have increased social distancing in the random environments. People are actively avoiding each other compared to where they would be just based on the asocial structure of the environment in this dashed line here. In the smooth environments, we don't see any effect of being in group versus solo. But this may be masking the simultaneous push and pull of social interactions. You want to be pulled towards people to potentially acquire more rewards, but you also want to avoid one another to some extent because you're competing for the same amount of rewards. And we'll get into this a bit more later in the modeling results. We also see that random environments increase the foraging rates, had higher foraging rates. They're destroying more blocks per second. Whereas in the smooth environments, people are more selective. They're spending longer between blocks. They're destroying fewer blocks, and the group rounds are being more selective here than solo. So the group environments amplify this activity. Now it was really nice actually that this previous work on Gibbons was introducing these kind of social networks based on proximity, and here we can also model proximity networks for each round, where the edge weight between each pair of players is based on the inverse distance, right? So people are closer together, we can define as being more related. And we can model centrality on this proximity network based on eigencentrality. And being more central predicted higher rewards in the smooth environments in green, but not in random environments. So when we're more close and more central in the social network, in these smooth environments, we're able to acquire more rewards, but only when the rewards are structured together, okay? So now I'm going to show you this automated transcription tool we developed to transcribe the visual field data. So on the bottom here, we have the screen recording of the task. And here we can take our data logs and recreate the task kind of at this live 20 hertz rates from each player's perspective, right? So here on the left is an overlay of the simulations versus the actual screen recordings. And the reason we do this is we can map each unique entity. So each block, each reward event, each player to a unique RGB value. And we simply read out the pixels on every frame, and we can determine whether that object was visible or not at a given point in time. And this allows us to develop these really nice visibility networks where these directed weighted edges are weighted based on the amount of time that a specific target player was visible from one player's perspective. And you can see these nice asymmetries in these networks. And these analyses also will inform the computational models I'll talk about a bit later as well, where we're using their exact visual field data to predict which blocks will destroy next. So I'll focus here on social attention, which is based on this visual attention analysis I just showed you earlier, where we can look at the out degrees of these networks as a metric of how much people attend to other players. So your out degree is kind of the weighted sum of all your of your outbound edges, and it's the more players you see, the longer you attend to other people, the higher this value will be, right? So this is how much we attend to other people, and we can compare random versus smooth, and we see that there's reliably higher levels of social attention in these smooth environments where social information is actually useful. So we see people adapt their social attention based on the reward structure. This higher level spatial intention had some costs. It meant that people destroyed fewer blocks, but this led to no difference in reward rate. So that kind of gamble at least paid off, right? You're just handing more to other people, you're foraging less, but you're being as successful. We can also compare the in degree, so how much people are looking at you, versus the out degree, how much you look at others. So we can think about this kind of x-axis variable as your celebrity factor, how much people are attending to you, and your y-axis as your popularity factor, how much you're peeking at other people. And while we see that there's general asymmetries in both, these asymmetries get reliably much stronger in these smooth environments where social learning has traction, right? So these asymmetries suggest more selectivity in who you're looking at. So the paparazzis are looking at the celebrities, and more specialization as well, right? People are specializing to being more social learners, these paparazzi on the left, and some people are specializing in these celebrities who are not really paying attention to other people. So beyond only modeling social attention, we're also trying to more directly model the causal structure of social influence. And one way we do this is to detect pull events from movement patterns. And this is inspired by methods used to study wild baboons by people like Ariana Scrounger and colleagues, where we're looking at candidate pull events from these min, max, min sequences in the pairwise distance between participants, right? So there's a lot of candidate sequences. So here's the one I'll illustrate below, but we have a min at T1, a max in their distance at T2, and then a min again. But we filter by a variety of different criterion. So the strength measures the change in the relative distance relative to the absolute distance. So it has to be a meaningful change in distance as opposed to just a wiggle at a distance, okay? Disparity requires that one player moves more than the other in each segment. And then leadership requires that one player, who's the leader, move more in the first segment and then less in the second. So here's the illustration of the pull event. I'm showing you kind of the state of the world at T3. But we'll start at T1, of course. So these players start out quite close to one another. The leaders in purple moves down to this corner here and starts finding some rewards at T2, which is just behind T3. I apologize for the readability. While the follower has moved over here to this corner, but hasn't really found any rewards. This player then moves down to imitate, right? And we consider this a pull event, okay? And because this player moves in towards the purple player, the pink player is the follower, purple player is the leader. So we can look at the frequency of these pull events where these solo rounds, again, provide a nice benchmark. How much of this is due to just the reward structure versus the actual social interactions? So we can run these analyses on the solo rounds. So we see like slightly higher amounts of pulls in the smooth environments. But when we use this to the baseline, we see a dramatically higher level in group, right? So we can attribute this just to the reward structure, right? Based on the common reward structure, there's some false pulls detected, but we see a really reliable increase in the group rounds where these are actually meaningful social interactions. And we see actually the opposite directionality for the random environments, that there's actually a decrease in the rate of pulls, okay? And here I've run a Poisson regression to model the rate of pulls, and we see that while there's a general decrease in group, counting for random, that the smooth group has a really reliable effect on creating more pulls. Now, these pulls are based on spatial data, but we can also relate it to the visibility networks, right? Where we can compute this leadership index, the number of times you're a leader minus the number of times you're a follower. So when you're a leader more often in these pull events, the higher leadership rates, and it correlates corresponds to in degree. So leaders are looked at more in the visibility networks. They look at others less. Leadership also predicts kind of the relative difference between in degree and out degree. And leadership also seems to predict a lower eigencentrality in this proximity networks, where leaders seem to be at the outskirts of the group, expanding the frontiers. And while leadership can do all these things, neither leadership nor in or out degree from the visibility networks predicts their ability to acquire rewards, right? The only thing that we can find, if we tried a lot of different things, is centrality, the spatial centrality, right? Being at the center of the group allows you to then more flexibly imitate, and that seems to be the only thing that really predicts reward. And While leadership itself doesn't predict overall performance, right? So here's your leadership score and here's your average reward, and we don't see really reliable trends. Leaders had higher instantaneous reward rates during pull events. So if you look at only the rewards acquired during a pull event, leaders had reliably higher rewards and followers. So it seems that social influence is modulated by success bias, but in this instantaneous level, as opposed to more long-term reward rates. So this will give us a bit of a behavioral summary. So first of all, I found that social learning is adaptive. We see more social attention in smooth environments. This came at the cost of destroying fewer blocks, yet this increased selectivity didn't affect performance. We also see that social attention was directed asymmetrically, with increased asymmetry in smooth environments. And beyond only attention, we also see more social influence events based on these pull events in smooth environments transpiring. And while social learning strategies such as kind of the in-out degree, capturing the relative weight for social versus individual learning, or leadership did not predict overall performance, leaders seem to have had a higher instantaneous reward rates during the pull events, suggesting some level of success bias selectivity imitation, which we'll model more explicitly in the next section. Any questions at this point? Yes. Yeah.
People were playing this at the same time, because it seems like the amount of people playing should have a big impact on.
Right. Yeah, so maybe it should have been more clear. So it's always 4 players at a time. So we have, yeah, so Yudu's asking how many people are playing at a time. And so we always had 4 players at a time, right? So these are groups of 4. We have 144 participants. I think this is, yeah, I think.
I guess 2 questions following up on that is why 4, right? Because this could, change your results a lot. And then the other thing is there a consistent leader throughout? Like, or do people kind of, I'm assuming that people take turns being the leader based on what they find. Is that more correct?
Yeah, so thanks for that. So I guess the first part was why 4. I guess dyads don't really seem to count as a group. 3 people also seems a bit asymmetric. So 4 seemed like the minimally viable way to study this kind of group behavior and really call it a collective or a group, right? So we would certainly like to do this in larger groups as well. And it's certainly possible, but this seemed like the minimal viable product to test this kind of collective social learning. And then the second question about consistency, we see consistency of in and out degree across rounds for the pull events because they're kind of sparser data. I guess what I can show you is like the x-axis shows the distribution of leadership scores. So people who are having a lot of these leadership events, right, seems to be quite reliable and also seems to correlate quite well to all these other measures of social learning based on the visibility network and the proximity network. So we think it's quite reliable, although because we're counting these discrete events, it's a bit hard to say how reliable it is, right? But right, so we do see, right, there certainly is some sort of trait-based aspect of leadership, but because we see a decrease in the amount of pull events, there's just fewer leadership events in the setting, right? So we see activity despite some innate distribution of these different strategies in the population. Great. Thanks. Actually, any other questions before I move on? I kind of enjoy having some more questions here. Okay, so then.
Yeah, super.
Yeah.
Thanks. Yeah, so one thing you mentioned is that there's sort of a, one cost that social learning incurs is smashing fewer blocks, right? But in some ways, it's actually decreasing cost. Like, in some ways, your average reward per block smashed is going up, right? So kind of your expected utility is increasing. And I'm curious what you think would happen if you actually increase the cost of smashing a block. So instead of it being like, what, a quarter second, pretty trivial to smash a block, it's actually like, you're trying to smash diamonds in Minecraft or something. Those take a long time. So, you could imagine that as sort of cost increases, people actually lean more on social learning because it's quite an investment to just kind of randomly find ones on your own. And so I'm just curious if sort of you run any versions like this or what you think might happen if you sort of mess around with the cost structure in the environment.
Right. Thanks for that great question. So I think we did a lot of testing to get to this kind of level where we got this kind of non-trivial question of, does it make sense to try to trial and error versus social learning? So you certainly push it in the other direction, right? Where you can really privilege social learning much more. It's not a quarter of a second, it's 2.25 seconds. So that's actually a substantial amount of time, given the whole round is only 120 seconds long, right? And so it's not that many blocks that you can destroy. But certainly I think you can push the dynamics even further. Here, as like the main focus is just the reward distribution. We're not changing the costs of foraging, right? We're just changing the reward distribution, and that has these kind of downstream impacts on the value of social information, which is the main focus here. But yeah, definitely other ways to manipulate it.
Hi, this is awesome, but I had to jump in because I was surprised by your answer to the why for whatever four objects on the screen, and I thought it was because there is a limit in the object tracking, like we can't track more 5 objects. So, but you don't seem to worry about it, and also because there is a limit in how many object we can track at a time. I'm wondering how this result would generalize to, a more, larger context where,
Right.
there are more.
So I think you're certainly right that as we move towards like more than just thinking about other people as individuals into situations where thinking about them as a crowd, right? That's kind of like unifying concept where we start thinking about their individual strategies and their individual differences in their social content, right? And we start to model them as a kind of a unified whole, as a crowd, and we'll behave quite differently there. So I think that's why 4 seems quite nice, right? We're not just a dyad, we're not just a triad, but we're not yet to this point where we're running into cognitive limitations and how we reason about other people, right? With this group of 4. So I think that suggests that we seem to have like the right size of a group here to study. Great. So if there's no more questions, I'm going to move on to the computational modeling. Okay. The goal of these models is to more kind of concretely test for different hypotheses about what matters in terms of how people select which blocks to destroy. So we're sequentially trying to predict which block participants will destroy at some time t+1 based on the kind of the state of the world at time t, but also using some past information as well. Okay. So last night at dinner, people were challenging me with the fact that computational models is sometimes a bit difficult to understand. So I'm going to really try here to make this very interpretable as possible. And we're trying to predict the probability that people will choose some specific block at time t+1 based on a softmax distribution of some set of features times weights. So this means that for any block, it has a set of features. I'll describe these features in the next slide. And these features then, this is a vector, and then there's some set of weights corresponding to each feature, okay? These are multiplied together, then summed. And then blocks that have a higher value will have a higher probability being chosen, okay? That's as simple as that. So these model features, F, capture hypotheses about both individual and social learning mechanisms, and I'll describe this in detail in the next slide, while we estimate these model weights, W, using hierarchical Bayesian methods in STAN, where we control for individual and group level differences at random effects. Okay, so here's the model features. So let's start with a snapshot of the task at some time 54 seconds into the task. And we're going to focus on this player here, who's the gray person. They started off in this corner and in this edge here and moved over here, okay? So the top row are asocial features, and these two are social features. In the end, we have our model predictions, but don't look too far ahead just yet, okay? So the first very simple asocial feature, we just look at block visibility, and this is a very simplified a way to look at visibility. We don't care about occlusion, so it's not so important because we use just this time t, right? Time t is the time they destroyed the last block. At that moment, we freeze time and trying to predict which block to destroy next. Okay, so everything in yellow is what's visible based on their gaze direction, and what's purple is not visible. So they're more likely to kind of keep moving forward and select blocks in their gaze visibility. We also have a locality feature, which is based on Euclidean distance. So you're more likely to destroy a block closer to you because there's a travel cost. As someone else mentioned earlier, there could be different costs. So if there's different travel costs, for instance, relative to the rate of destroying blocks, this locality feature may have a different weight. Then more complex asocial learning features that based on the blocks that that participant destroyed. So they destroyed these 3 blocks here of no reward, and then this nice big healthy cluster of blocks there in blue. And we're trying to predict which other blocks that they've not explored yet will have a reward, right? And so yellow indicates a higher probability of reward. So what's a GP? Well, this is a Gaussian process model that I've used in a variety of other papers before to model human learning in spatial, conceptual, and graph structure contexts, where the basic idea is that this is a type of function learning task, right? We have some input dimension. This could be some spatial location, some arbitrary set of features like the tilt or stripe frequency of these Gabor patches, or just which node ID it is based on a graph structure. And the idea is we have a couple observations about reward, and then we're essentially generalizing to other unobserved options, similar to how we interpolate or extrapolate when we're learning a function, right? We see a couple dots, we can then extend the line further. Now, these experiments have used this in a continuous reward learning paradigm, whereas here we have discrete, it's reward or no reward. And so all we do is essentially we transform this Gaussian process model with a sigmoid function. So we're now, instead of learning the exact reward value, we're learning some latent variable z, z for the Americans, which when this variable is higher, the probability of reward is higher, right? So essentially, the colors here correspond to this latent variable. So when it's yellow, essentially our model corresponds to predictions of higher probability of reward. Okay, so here are the predictions. So these are the asocial learning features, and these are mainly used as sanity checks, right? These are all essentially counting for all the ways that individual learning could inform how people select blocks. But then we also have these social features here. And this is based on our visibility data again. And they're both forms of proximity, okay? So first, we categorize people as being visible or not visible in this time between t-1 and time t, right? So at time t, this is the last block I destroyed. I'm going to predict the next one. t-1 is the block previous to that. In this time window, we're trying to categorize which players are visible. Then we distinguish between them as being successful or unsuccessful, where successful means I've seen them, I've also seen them find a reward, okay? And so then I've just plotted that in this case, there's one successful player here, and then there's one unsuccessful player here. Both are visible from this gray player's perspective, or were visible within this time frame, t-1 to time t, okay? And then we have a simple proximity measure, sorry, tease the results. Then we have a simple proximity measure, based on, oh, this is almost dead, based on their last seen location, right? So it's not their actual location at time t, but where they were last seen. So we essentially assume that that was the last time they had information about them. And if there's multiple players in each of these categories, then we essentially define a centroid of their last seen locations. These are then all multiplied by a set of weights. Here I'm using the kind of the group level, population level weights here to make to define the model predictions here, where yellow corresponds to higher predictions about where they will search next, and X is the actual choice that was made. So here are the model results. So essentially the X-axis showing the population level estimates. So very simply, in the block viz and locality conditions, we see that they matter in all conditions, and they're typically somewhat stronger in random than smooth environments, right? So the orange compared to green. And this is probably because there's no other kind of reward predictive features in the environment to go off of. So you might as well just choose what's available to you, what's visible, what's local. We also see that the GP predictions are very strong in these smooth environments in green here. I should also mention the black dots are just this kind of contrast between smooth versus random, okay? So when it's to the right of this dashed line, it's where smooth is had higher estimates than random. And here, you see really strong effects in smooth environments, but they're null or negligible in random environments because there's actually no reward structure there. So it's the wrong model to use. Now here, I was going to shift everything up. Here are the weights for the social, successful and unsuccessful proximity, and we only have data here from the group rounds because it's not possible to run this for the solo rounds, where we see that successful players attract much more in the strong environments, right? There's much more of a weight on successful proximity, and that there's no influence of unsuccessful players, right? So this categorization of a successful versus unsuccessful was very important because there's no influence of unsuccessful players, but really it's successful in the sense that influence people. But there still is a persistent and reliable traction of successful players in random environments, even though there's no value to social information. So this might be a bit of a success bias that persists even when the environment doesn't call for that type of bias. We've also tried a variety of alternative models. So we have an asocial model, which ignores all social information, and that's much worse. Here I'm showing you the protected exceedance probability, which is this kind of Bayesian modeling framework showing which probability the best model. So this kind of summarizes all our model results where higher is better. We also tried an unbiased model where we didn't distinguish between successful versus unsuccessful players. They're all lumped together into this one notion of visible player proximity. And this was also much worse. The success bias model in green is what I showed you previously. But we also ran another model where we had unique social proximity weights for each player, right? And this is a fit hierarchically within each group. So me as a player, I would have one attraction weight for the 3 other players in the group. This was also fit quite well, but not as well as the success bias model, but still seems to warrant some attention. And so I've looked a little bit into these weights, right, and tried to relate this to other aspects of the data. And just to keep in mind, this weight is how much I, as the target focus player, am attracting others in my group, right? So we see that in smooth environments, the higher this weight, the higher I'm attracting the people, the higher my score. So it seems that people are biased towards people who are performing better. I'm showing only the kind of the reliable estimates here, and this is only for smooth environments. We don't see any effective foraging rates or centrality. We do see effective in degree, right? So the people who are imitating the most are also being looked at the most, right? This seems to correspond, even though we're kind of using different data to estimate this. And we also see that the people who are being imitated the most are also tracking with leadership score. So these 2 different types of analyses are converging on the same evidence, where the same people are being leaders and also have the highest imitation weights. The last type of analysis we're running on this data is still a bit of a work in progress, but it's a simulation-based framework where we've simplified the task even further to this kind of 2D environment here, where we can use potentially counterfactual model weights to define destinations for these agents, and then we can simulate these agents and their trajectories and their visual fields on this 2D simplification of the task, where what we would like to do is we can ask questions like, what would a homogeneous balance of social versus individual learning look like versus heterogeneous specialization? We can lesion away aspects about their learning strategies, right? We can change the selectivity biases, and we can look how that influences group and individual performance. So this is a bit of a work in progress, but these light green agents in the top left are success-based imitators. And these green agents here are kind of these baseline asocial learners. And what you can see is like these green lines that move out from them are showing their destination. So these agents, reset. These agents are moving towards the destination at each time t, similar to the way our model is defined. But I think we'll see quite soon that you'll see these kind of gray lines that come out representing when an agent sees a success event, and then that's determining on this next kind of decision node where it will forage next, right? So we're kind of building in all the components of our model into the simulations to then try out different weights as different kind of social learning mechanisms to see what would counterfactual strategies, how counterfactual strategies and populations perform. All right, so in summary, I've shown that social learning is both specialized and selective. We see that there's these asymmetric social attention structures based on visual data, and this suggests a diversity of strategies in the population. So it's rather than this kind of notion from Rogers paradox that everyone converges to this homogeneous mixture strategy, we see a lot of diversity in our populations. We also see that there is success bias activity in social imitation. Yet for all these biases and kind of the specialization, people still adapt within the kind of this baseline to the demands in the environment. So we see that in smooth environments where social information was actionable, people had more social attention. They spent more time looking at other people, despite the fact that it's reduced their foraging rates. And we saw more social influence events based on the poll analyses. We also see that this success bias increased substantially in smooth environments, where it was actually seem ecologically rational, but it still nevertheless persists in random environments, which could just be the fact that we're not able to completely account for this bias that generally works quite well. And I've teased a bit of this future direction we're still trying to finish up now, which are using these agent-based simulations to test for counterfactual model weights, where we can try to lesion out kind of key aspects of our social learning behavior here, such as specialization and selectivity bias. So thank you for your attention, and I'd like to thank my collaborators, Dominic Deffer, MPI Berlin, Benjamin Call, Björn Mader, Marco, and Ralph Krivers. And now it's time for questions. Thank you.